This is intended to be an introduction to reinforced concrete design. And because it is an introduction, it will not contain all of the information that you will need. However, it will be, as I say, just that. It will be an introduction. So here's a basic outline of the information that we're going to cover. We're going to have a little bit of introductory material, some information about the materials that make up reinforced concrete. We will discuss the concept of ultimate strength design, beam design, columns, slabs, and footings. And each of those, of course, will be at an introductory level and will be fairly brief. There will be some other videos that I will do that will back up this information with some more details later. So first off, it's important to realize that concrete is good in compression, but is very bad in tension. And so when you are designing a structure with concrete, you will add reinforcing steel in those locations of the concrete where it is in tension. By doing that, you will have steel that can take the tension loads where the concrete is not so good at doing that. As a result, you're going to end up with a composite material. This composite material is made up of the concrete and the steel reinforcement. Essentially, when we do that, we are making in the plywood formwork that we might have to cast our concrete in, we are essentially making custom-made columns and beams with steel reinforcement. These are not off the shelf. They are custom-made, so we get to decide what the size of the columns are and what the size of the beams are, and also where the steel is going to be placed in those items. Lastly, I want to clearly say that this presentation is based on the latest American Concrete Institute code, which is 318-14. Now, we're going to talk a little bit about materials. And first off, we are going to talk about concrete. And one of the most important things that we use as a material property for concrete is its ultimate strength. And this is its ultimate compressive strength. And we usually denote this with the symbol F sub C prime, which is usually in the range of 2,500 to 5,000 psi for regular structural concrete. Now, it is possible for it to be much higher than that, but these are some common ranges for the ultimate compressive strength of concrete. Now, if you're going to be doing a project in the United States, a common value that would be easy for you to get is 3,000 psi, and so I would recommend that. Of course, higher values are okay too, depending on the situation. If you're doing a project in a third world country, then because sometimes the quality of concrete is not quite as good, then when you are doing your calculations, you probably would want to use something like F sub C prime equal to 2,500 psi. Now, the modulus of elasticity for concrete can be calculated according to this formula here. E sub C is equal to 57,000 times the square root of F sub C prime, and the resulting answer will be in psi. Now, it's important to realize that whenever you see in the formulas that you will often see in the code book, whenever you see those formulas have F sub C prime under a square root symbol, it's important that you use F sub C prime in psi units. Now that might look strange to you because when you take the square root of something that has psi units, you're getting the square root of psi units. But these are empirical formulas. They have been experimentally determined, and so the formulas do work out, even though it looks like it doesn't work out. the answer will come out in PSI, even though we have this thing inside square roots. But just always remember PSI units when you put it in the square root symbol. Don't use KSI units for F sub C prime when it's under the square root. Lastly, as you know, when you are designing a structure, you do have to calculate the weight of the structure itself, and that, of course, contributes to the dead loads. For normal weight concrete, it is common to use 150 pounds per cubic foot. Now, that is what people use all the time. That includes the concrete, and it already includes the reinforcement that is included in the concrete also. For reinforcing steel, there are a variety of grades of steel that are available. I'm only showing two such grades of steel on this slide, but they are the ones of grade 40 and grade 60. Those grade values are referring to the yield strength of those steel bars, 40 KSI and 60 KSI. In the United States, it's common for most of the rebar to be 60 KSI, and of course then you would specify that on your design drawings. The recommended value in third world countries is probably best to use Fy equal to 40 KSI. The reason for that is that sometimes in third world countries they don't have the higher strength rebar as readily available, and so I kind of recommend that you use this one. We also have here the modulus of elasticity for the steel, which is 29 times 10 to the 6 psi. The last thing I want to say about the reinforcing steel, at least on this slide, is that it's important to provide what we call clear cover. And basically what this means is how much cover with concrete is there over the rebar. And so there are a variety of requirements in the code for this, but one that is typical is that for a concrete column or a beam that's inside a building, the distance from the outer surface of the concrete to the edge of the steel should be at least 1.5 inches. And so in this way, the concrete is not only taking compressive loads, but it is also actually providing some protection to that reinforcement, protection from erosion and corrosion and things like that. So it's important to provide adequate clear cover, and it is even a code requirement, and you can see more information about that in the code in section 20.6.1.3. Here's a typical concrete stress strain curve. In fact, there are several of them, and so you can see there's a somewhat linear portion. It gets to its peak value and then it rapidly loses strength. In fact, this can be really rapid strength loss, sometimes even explosive. So there's not a lot of ductility in concrete. These are relatively small strains compared to what we're going to see for steel on the following slide. Remember though, this value here is about 0.003, and when we look at the next slide, we'll see how dramatically more ductile steel is than concrete. The concrete stress strain curves would probably only be going up to this distance right here. So it has dramatically less ductility than the steel. These strains over here are much bigger than 0.003, which we saw was around the ultimate strain for concrete. So as I said before, some typical steel grades are 40 KSI and also 60 KSI. And those have a good amount of ductility, which is an important thing that we rely on when we are designing reinforced concrete structures. Now, when we talk about rebar or reinforcing bars, we often specify them in terms of a bar size. And these sizes are a variety of numbers. Number 3 all the way up to number 11, and then there's a number 14 and a number 18. These numbers indicate how many eighths of an inch there are in the diameter of the bar. So for instance, here's a number 5 bar. It has a 5/8 inch diameter. And that kind of idea works for all of these bars. So this is a nice table because it gives you the diameter, it gives you the bar size, but it also gives you the cross-sectional area for each bar size. And so, of course, you will refer to that often as you are doing design calculations for beams and columns and so on in design. The next thing that we need to look at is that we will be doing what is called ultimate strength design in reinforced concrete. And it's basically the same as LRFD that you learned about in a steel design course. And so basically we have here that the nominal factored resistance needs to be greater than the sum of the factored loads. And so of course we have phi factors, which are the strength reduction factors, and you can see those in code section 21.2. And then you also have load factors, which can be seen in code section 5.3. A very brief example here is that if we have a column, we want the phi PN, the nominal factored axial capacity of the column, to be greater than or equal to the sum of the factored loads, which can also be denoted by P sub U. This is just like we did in steel design. Now, the next thing we'll look at here is a brief introduction to beam design. And we want, when we are considering beam bending, we want for phi mn to be greater than or equal to M sub U. And so, of course, a person is going to have to calculate this quantity, phi mn, so that it can be compared to the factored moment, the worst factored moment in the beam. Now, in this example, I've shown a simply supported beam and some sort of loading. Here I have a point load, but it could be anything. And I also have shown here section AA. This section is showing a generic cross-section of a beam. And you'll notice that, of course, we have a width for the beam, which is denoted by the letter B. We have a height H. We also have a distance D, which is the distance from the topmost compressive fiber of the beam and down to the centroid, or the center, of this layer of steel reinforcement. That distance D is going to be showing up often in our formulas, and B also will. We're also going to have A sub S, and that is the area or total area of tensile steel reinforcement that's down at this layer at the bottom of the beam. We certainly know from basic mechanics that the bottom of the beam is going to be in tension and the top is in compression. So that's why we put the majority of our tensile steel down here along the base of the beam, and we're seeing that here in the cross section. Now, it is true that we could have more than one layer. We can also have bars up in the compression zone, but for right now I'm keeping things simple, and the formula for phi mn that I have here only considers this tensile layer in the calculation of phi mn. Later on, when you learn more, there will be additional ways to calculate Phi-Mn when you have other layers of steel, but for right now this is quite adequate, and for many beam bending calculations this will do very well. So here we have Phi-Mn. It is calculated as Phi times the total area of tensile steel times the yield strength of that tensile steel times this quantity in parentheses, which is D minus A over 2. Now in a little bit we're going to learn what A is, but for right now let's look at some of these other items here. For instance, we have Phi, and it is going to be equal to 0.9. And it will be equal to 0.9 when the strain in the tensile steel down at the bottom of the beam is greater than 0.005. Now you can establish what the value of epsilon sub t is by using this formula here. It is D minus C over C times epsilon sub u. Now throughout all of reinforced concrete design, the code says that epsilon u is 0.003, and this C value that is mentioned here is equal to A over beta 1. And for much of the concrete that you will design with, beta 1 will be 0.85, so you know what that value is. And A, this quantity that I mentioned we would learn about, is calculated with this formula here. It is A sub S times F sub Y over 0.85 F sub C prime times B. Now, as I said, this is an introductory discussion of beam bending, and you may not understand exactly how we get this formula and how we get A and all of this kind of thing, but this is just introductory, so I'm not going to get into that, but suffice it to say, this formula here will calculate Phi-Mn for you, and it needs to be greater than or equal to M sub u. Now here are some additional rules for beam design. For instance, these are rules specifically regarding A sub S. The steel ratio is defined as rho equal to A sub S over B times D. Now I want you to notice that this is not B times H, the full height of the beam, but it is B times D, and this is often referred to as the steel ratio, and you will see that come up from time to time in the code book, and so that's an important concept. We also have for our tensile steel some limitations. For our maximum area of steel, we can know whether or not we are below the maximum if epsilon t is greater than 0.005. So you always want this to be true. Now there are some exceptions to that, but to keep things simple, I always tell people always make epsilon t greater than 0.005. And if you do that, you know that you have not exceeded the maximum allowed steel. So just do it that way. Secondly, there is a minimum amount of steel that we want to have. And this comes about by this inequality here. We want rho to be greater than the minimum steel ratio. And that minimum steel ratio can be calculated by this set of equations here. And basically, we want the larger of these two when we calculate rho minimum. So whichever of these is bigger is the value of rho minimum, and we want our steel ratio for our particular beam to be greater than rho minimum. The conclusion of this particular slide is that the concrete code has limits on the amount of tensile steel. Too much steel is bad, and too little is bad also.